Tonight's program, Black Holes and Holographic Worlds, a wonderful program. Black holes have really, over the last few decades, played a vital role in helping us understand the universe with ever greater detail, ever greater precision. And tonight's program, wonderful moderator, Alda, who will be out in just a little while, my friend Robbert Dijkgraaf from University of Amsterdam will be giving you an introduction to the subject in just a couple of minutes. And to ensure that everything you hear tonight is absolutely accurate, absolutely spot on, we have a very special member of the audience, the world's expert on black holes, Professor Stephen Hawking. And so without further ado, I'm proud to present to you Black Holes and Holographic Worlds. Thank you.
Good evening, ladies and gentlemen. My name is Robbert Dijkgraaf, and my pleasure and honor to, and also I must say a little bit of a sinking feeling, to teach a short Black Holes 101 course in front of Professor Stephen Hawking. Must be the most intimidating audience, just in himself. Today we will not only discuss the edges of space and time, but we actually bring you also to the edge of current research, of the great questions and ideas in understanding space, time, information, gravity. And in fact, we also see that black holes are right there, where the two main characters, the two big theories in modern physics, general relativity, Einstein, that describes the large structures in the universe, and quantum mechanics, that describes atoms and even elementary particles, how they clash and where they clash, and black holes are right there in the middle. So just as a little teaser trailer, let me flash some of the important points that we will be discussing. And let's start with the history. Black holes actually made a long journey from an idea to a full theory, and finally to a physical, observable phenomena. Already in the end of the 18th century, the French astronomer Laplace discovered that if an object is heavy enough, then even light, which is the fastest traveling object, a phenomena in nature, cannot escape. But of course, there was only Einstein, with his theory of general relativity, the fundamental description of space and time, where they found their proper place. And the first mathematical solution was found in 1916. And then John Wheeler, the famous American physicist, really brought this subject alive in the 1950s and 60s. And in fact, he also baptized it as a black hole, because a time or null-like geodesically incomplete solution of the space-time equations makes it a little bit difficult to pronounce. If you look at black holes, I mean, one thing we can do, I can take a little marble and throw it up. And of course, it will fall back to Earth. And you can wondering, how fast do I have to throw the marble so that I can throw it to the moon? It has to escape the gravity of Earth, and it has to have a speed of 25,000 miles per hour. But now you can ask, can we make the Earth heavier? Or what we can also do, shrink the Earth, make the mass more concentrated, and thereby strengthen the gravitational force. So how small should we make the Earth so that even light cannot escape? And the amazing thing is that the Earth would be as small as another marble. But then a marble that would weigh as much as the whole Earth. Now, this is a very caricature of a black hole. But a better way to describe it, of course, is Einstein's equations. Einstein's equations that tell us that space and time are curvature generated by energy and mass. So it's like the stage on where I'm standing is not rigid and flat, but actually is made out of rubber sheet that curves under the influence of mass. And if you have enough mass, then actually the whole thing will turn into itself. it will essentially, the space-time will curve in such a way that it stops objects from escaping. In fact, what will form is what technically is called an event horizon, a sphere surrounding the singularity, the place where everything gets crushed together, a sphere that surrounds that singularity that divides space-time in two regions. The outside, where everything is safe and things can escape, and the inside, where things are doomed. And they're doomed in a fundamental way because inside the black hole, there's only a limited amount of time. It's like you're watching a DVD and you know there's only 10 minutes to go, so the plot better come to a good end. Black holes are, of course, absolutely fundamental in understanding our universe, and therefore it's important to see where we can find them in the universe. And I want to mention 3 examples that we'll discuss in much greater detail later today. The first are black holes which are roughly the size of a star. If you have stars which are heavier than the sun, at least 3 times heavier, or typically 10 times, at the end of their life they will explode, and the remainder will collapse and will form a black hole. If you are kind of lucky, and the black hole is part of a binary system, there will be another star orbiting the black hole that can feed off its energy and mass and all the matter. It will swirl around the black hole and will emit X-ray radiation. There are now many, many examples of sources in our galaxy of these star-like black holes. But there's a second category, which is even more fascinating, which are black holes that are sitting right in the center of galaxies. And it looks like almost every galaxy had such a black hole. And the plumes of radiation that are coming off are so large that, as you can see in this picture, they're even larger than the galaxy itself. Hundreds and thousands of light years of energy radiating out of these galaxies. And if you move inside the galaxies, and we can do this by watching with our telescopes, you will see that inside the galaxies there is these huge black holes that are millions or sometimes billions times more heavy than a typical star. And just to give an impression of how forceful these objects are, even these galactic centers, these supermassive black holes, which are 1,000,000 times heavier than the sun, they're not that big. They're perhaps 4 times bigger than our sun. So much energy in space is concentrated. And we also will discuss a third type of black hole, which is even more mysterious. Because, as I said, a black hole is not necessarily large or small. It can have every size. But what about if you took a black hole and made it as small as a particle? Could a proton or electron be a microscopic black hole? Well, to ask that question, we actually have to marry the theory of general relativity with quantum theory. And this is where one of the most important achievements of Professor Hawking was made. Because he realized that if you take tiny black holes, you really take into account the quantum theory of matter, the things, the laws that govern the smallest particles, then actually black holes are not black. They start to radiate. There's a possibility of matter escaping the black hole, and thereby the black hole can evaporate, and in some sense it looks just like a particle that's formed and again decays. But if we take that last step and really ask these kind of questions, we are really no longer in the realm of observations of good answers. We are really at the stage where we should ask good questions. And I think there's nobody better to ask these questions than Alan Alda. Thank you very much.
Hello, thank you. You know, I was at my computer this morning trying to get up to speed for tonight. And an email popped up on my screen from my daughter Eve. And it required a long answer. And I said, I just shot back an answer quickly, and I said, I can't answer you right now. I'm trying to learn everything that is known about black holes in the next 2 hours. So, being my daughter, she shot back an answer to me, and she said, "You need the whole 2 hours?" So then she laid it out for me. 1, there are areas of space that suck everything into them. 2, you don't want to get near a black hole. 3, some people are like black holes. They suck everyone around them into their vortex. And she ended with, what else do you need to know? So that's really the question, isn't it? What else do we need to know? We've heard about them. We know a little bit about them. We use them in conversation. Sometimes we make jokes about them, the way Eve did. But what really are they? What are these holes? How do they form? And how can they tell us something about the universe that's unexpected? Well, we have an extraordinary panel tonight that can guide us to the heart of black holes and throw some light into dark places for us. Please welcome Kip Thorne, Raphael Bousso, Andrew Hamilton, and again, Robbert Dijkgraaf. Welcome. Let me tell the audience a little bit about each of you. Andrew Hamilton on your right. On your far right is an astrophysicist known for his scientifically accurate general relativistic visualizations of black holes, which have appeared on a number of TV documentary programs, including Nova and National Geographic. His computerized renderings, which take viewers into black holes, utilize video game software developed by Silicon Graphics. And they're based on Einstein's equations, and they're designed to visualize the unseen. Dr. Hamilton is professor of astrophysics at the University of Colorado, Boulder, and a fellow and current chair of the JILA Research Institute. Did you say JILA? Gilla. Thank you very much. I never heard that before.
We have 3 Nobel Prize winners.
I bet. There's going to be a lot of things I never heard before tonight. So, Robbert Dijkgraaf, no, wait, now I'll do first, next on your right is Raphael Bousso. Raphael is known for discovering a general relation between the curved geometry of space-time and its information content, which we're going to get into tonight in a serious way. And that's known as the holographic principle. You say holographic or holographic?
Holographic.
That sounds like both at the same time. This is amazing. This is like quantum mechanics. You know, you get everything at once. What?
I'll let you pick. What do you prefer?
I'll pick it. Holographic.
Holographic.
Yes. Okay. I don't want to hear anybody else say it any other way tonight. This holographic principle is believed to underlie the unification of quantum theory and Einstein's theory of gravitation, those two things that don't seem to go together. Dr. Bousso is professor of physics at the University of California, Berkeley, and he's one of the discoverers of the landscape of string theory, and his work has led to a novel view of cosmology, the multiverse string theory. And we're only going to appear in one tonight, as far as I know. Next to Andrew is Robbert Dijkgraaf, who has done award-winning research on string theory, quantum gravity, and the interface between mathematics and particle physics. He's dedicated to creating greater public awareness of mathematics and science and to bridging the gap with the arts and humanities. That's great. I'm really glad to hear that. He's president of the Royal Netherlands Academy of Arts and Sciences and is the distinguished university professor at the University of Amsterdam and the chair of mathematical physics. And to my left is Kip Thorne. Kip is a prolific expert on gravitational waves and is the co-author of the textbook Gravitation, from which most of the present generation of scientists has learned general relativity. His research has focused on relativistic stars, black holes, wormholes, time warps, and gravitational waves, and he co-founded the LIGO, which, as you know, is the Laser Interferometer Gravitational Wave Observatory.
That's why we call it LIGO.
Oh, yeah. And Kip is a member of the faculty of the California Institute of Technology, has been since 1967, and Kip was the Feynman Professor of Theoretical Physics from 1991 to 2009, and he helped me enormously with notions of quantum mechanics when I played Richard Feynman on the stage. I'll always be grateful for that. Well, welcome all. Let me just see if I know anything at all about a black hole. Let me correct me on this. This is the impression I get from general reading. You start out with a pretty big star, and it's got a lot of gravity, and it's pulling in all the stuff that the star is made of because of the gravity, but it's also radiating energy. And if it radiates enough that the gravity is more of a pull than the radiation pushes out, the star collapses and becomes a black hole, and then not even light can get out of it. How close is that?
Close.
Okay, correct it a little.
No, that's a great way to say it. Let me say it in a different way that you may not have heard, but another way of thinking about it. I like to talk about Einstein's law of time warps. Einstein's law of time warp says that everything likes to live where it's going to age most slowly. And gravity pulls it there. And so you age more slowly if you're on the surface of the Earth than if you're at high altitude. And so that's why gravity pulls you to the surface of the Earth.
So it literally clocks run slower.
And that causes
but so little slower, you wouldn't notice it unless you
No, but that's enough to produce the gravity that holds you to the Earth. So little, 4 parts in 10 billion slower here than up at high altitude. But that's enough to produce the gravity that holds you to the Earth because you want so badly to age more slowly, even if it's only 4 parts in 10 billion. Okay. So we've got that.
Yeah, that's good.
Okay, so now you've got a star. And time is flowing more slowly on its surface. And as you say, the heat, you're radiating away the heat that is holding it out, and ultimately it implodes because gravity wins. And as it shrinks smaller and smaller, gravity becomes stronger and stronger at its surface, and correspondingly, time flows more and more slowly. And ultimately, it reaches a size where gravity is infinitely strong at the surface, and time is flowing at 0 rate. That's the horizon.
0 rate, so time disappears.
If you try to hover above the horizon, if you try to hover...
Why don't we say the horizon? Maybe get a...
Oh, I'm sorry. I screwed up.
Okay, the horizon, I mean, not everybody may know. This is the region at the outer edge of a black hole?
It's the surface of the black hole.
Right, and when you pass that horizon, that surface, then you're in the black hole, and you can forget everything after that.
But now let me tell you a point of view on why you can't get out.
Okay.
So if you hover just above the horizon, time is flowing exceedingly slowly, basically not at all. Something weird has to happen to time when you go inside the horizon, because after all, it has stopped flowing if you're just above it. What happens is that time starts to flow in a direction you thought was a space direction, toward the center.
Anybody get that?
Somebody over there.
Is there a picture of it there? Oh, no, ask him.
No picture yet. No picture yet.
But they got a picture of something.
Yeah, well, we'll come to this in a moment.
Okay.
But that's why you can't get out of a black hole, because time is flowing toward the center, and you can't go backward in time.
Well, that I knew. I came in knowing that.
Yeah. But if time is flowing toward the center and you can't go backward in time, you can't get out of a black hole.
How does time turn into a direction? What did you say?
Well, it's the weird thing about relativity, the weird thing about Einstein, that a direction you thought was a space direction. Yeah. Inside a black hole, it's really a time direction. Mm-hmm. And you are forced always to move forward in time, so you're dragged willy-nilly toward the center of the black hole, and you can't get out, because to get out, you had to go backward in time.
And time reaches a point at the center of the black hole where it doesn't exist anymore.
Well, you get to the center of the black hole, and you have a singularity. We can discuss that later and Andrew may give us some visualization.
Right.
That's where you die.
What? But I wanted to get to where I would age slowly, and now you got me dead.
Yeah, you want to age slowly, you got to stay outside the black hole and hover.
Okay, so they could make face cream out of these little black holes, I guess.
Okay. Sorry, I got you off on a digression.
Robert, let me ask you, were these black holes around at the time of the formation of the universe? Would you rather ask? Yeah, sure. That's
Well,
Raphael.
not as far as we know. It's possible there's some speculations about what might have happened in the early universe that include the formation of very small black holes. But the black holes that you discussed could only have formed after the first stars formed and burned out their fuel, so that what you described happened. That the radiation no longer holds them up, and they collapse in on themselves.
They pretty much only occur as a result of a star burning out its fuel.
Yeah. So the earliest time would be millions of years, probably, if not. Yeah, certainly the ones that most of the ones we see would be much older, much younger. Would have formed much longer after the beginning.
Andrew, what about the stars there's a black hole at the center of the Milky Way, right?
That's right.
We know that for sure.
It's probably the best observed example of a black hole, of what astronomers call black holes. We don't actually see the thing looking like a black hole because it's way too small to see. But we do see, Andrea Ghe's group at UCLA in particular sees stars buzzing around a place that corresponds to the center of our galaxy. These stars are buzzing around, and we can tell from their orbits, or she can tell from their orbits, that what is there is weighing in at 4 million times the mass of our sun, and yet it shows no light in the infrared. You have to look in the infrared because you can't, if you look in the visual, dust and gas gets in the way. So you look in the infrared, you don't see any stars there. You see a 4 million solar mass thing providing the gravitational pull, which is causing these stars to go around.
I think we actually have a movie of this from Andrea Ghez.
You have a movie of this?
Yes.
Oh, that'd be great.
There we go.
Okay.
So you see...
Where's the black hole?
So, well, look at what everything is going around. You see...
Everything looks like they're going in different directions.
It's the star. It's the star thing. Each of those round things is a star.
Let's replay it. Let's replay it.
I mean, I know a black hole is black and you can't see it, but
these are the orbits of stars going around that thing that you saw something came in, it whirled right back out, right where that star is at the center.
Yeah.
Another object went around it in a more elliptical orbit.
Now,
but you don't see the object. They've put a star in there. They should have put a black hole in there.
Right. Well, are some of those stars going to eventually get drawn into the black hole, do you think?
Andrew?
Well, the stars that we see are actually the ones that have survived. They don't get close enough to be tidally torn apart. But presumably there are stars, or there were stars, that got a little bit too close and got tidally torn apart. And once that happens, the gas that they were made of is going to stream into the black hole.
Now, my guess, hearing that, is that the black hole has, at the center of our galaxy, has some kind of structural significance. It's at the center of the galaxy. Is it holding the galaxy together in some way, or what?
It's too small by itself. It's a mere 4 million times the mass of our sun.
Yeah.
And the galaxy comes in at hundreds of billions of times the mass of our sun. So it's just a small piece of our galaxy. But it certainly dominates the central region of our galaxy. Its gravity is dominating the gravity in the central region.
Will you always find a black hole? When you observe a black hole through this indirect process, when you observe that there's a black hole in a galaxy, will you always find it in the center?
No, we see two types of black holes. We see supermassive black holes like the one at the center of our galaxies, and those always seem to be at the centers of our galaxy. Now, I'm not sure whether that's really always true, because the astronomers tend to look at the centers of galaxies where they expect to see these things. But we also see stellar-massed black holes in the Milky Way, and those are not at the center.
I see. So my impression, because they're in the center, thinking everything's swirling around them, they got there some other way. It's not. I mean, it's not that they're causing this this galaxy to form around them.
Oh, they certainly have a tremendous influence on the galaxy surrounding them, and they may well moderate star formation in the galaxy as a whole. But we think that those central black holes, we don't know for sure because we haven't seen one form directly in front of our eyes, but the leading idea is that they formed in the usual way, you might say, from the core collapse of a massive star, and then accreted gas from the surroundings. So the center of a galaxy is a very special place. It's a place where gas tends to funnel down to.
And you said they accreted gas, and that is tied to the term accretion disk, right? Where you can tell a black hole is there in part by seeing stuff light up as it falls into it. Is that right? Is that an accretion disk?
That's about the only way we see them,
I see.
by virtue of the stuff that falls onto them.
So where, Kip, this is, does this come out of Einstein's theory fairly directly, the notion of a black hole? Did he predict it?
So it comes out of his theory so directly that it was the first mathematical solution of his equations that anyone ever found. Karl Schwarzschild, a great German astrophysicist, found it a matter of months after Einstein formulated his general theory of relativity. However, it wasn't well understood at that time. We had this mathematical solution that described something, but everybody thought of it, well, this is the external gravitational field of a star, but if you look at the mathematics of it and you take away the star, there's still something there that's pulling gravitationally. And it was really not until the era of, and the work of John Wheeler and colleagues in the late 50s, early 60s, that we really understood clearly these black holes. Even though the mathematics mathematical solution, Schwarzschild's solution, had been around by then for nearly 50 years.
That's interesting. So people knew about it, but they didn't believe in it, or what?
So it was just very hard to get a physical handle on the meaning of the mathematics when the mathematics is saying that time is flowing in a direction.
Well, I can understand the difficulty, there is, and we can get to this in more detail, but Professor Hawking's Hawking radiation seems, when I hear about it, seems to go against the idea that nothing is coming out of a black hole. Can you say that Hawking radiation, is that coming out of the black hole, or is it coming off of the black hole? What would you think?
Well, it's actually usually one way to understand it is that, quantum mechanics allows for a brief time to have a pair of particles to be produced, a particle and, say, an antiparticle. And if that just happens very close to the horizon, one can kind of fall in and the other can get out. And it's even more bizarre because the particle that falls in has kind of negative mass, so it eats up a little bit of the mass. So if you really are asking where anything is coming out, I think that's, in some sense, that's already a caricature of the calculation, of course, but then it's not really something that passes through the horizon.
It's not coming, when we hear about Hawking radiation, it's not something that's coming from inside the black hole, going through the horizon and coming out the other side, right?
No, that's not.
It's something that's happening on the surface, at the horizon, right about at the horizon.
That's a good way to think
and it's
about
coming off of the,
yes.
and this can be measured, right?
Yeah, so Jessica, maybe the Hawking radiation slide will help you describe this.
Jessica's searching through her slides. She didn't expect this at this point. You see, this is when you have somebody who's just curious and not organized, you get this.
Okay.
Is that it?
So, so you might, I don't know whether you can see it. Do you want to comment it, or I'll just repeat what you said?
It's your picture. It's such a beautiful picture.
Okay, so if you look on the left, ignore the thing on the right. On the left, you see two astronauts falling into a black hole, and they're watching what happens when Hawking radiation is created.
Yeah.
And what you see happening is that there are a particle and antiparticle pair that are forming. You see, say right at the very top of the left-hand side, you see an arrow with the particle that's flying out, and another arrow with the particle that's flying in. They're very close to each other. They've been created as a pair by the intense gravitational field of the black hole. They've been pulled out of nothing. And the one goes out and it becomes part of Hawking radiation. The other one goes inside the horizon and is lost. And this can only be done in pairs. This is.
I was going to ask you why, and I think you answered it just now. Why am I right about this? These are paired particles
Yes.
that pop in and out of existence all the time.
Right here.
Right now.
This room. Yes. So the amazing thing of understanding the quantum theory of particles is that even empty space is very active, because continuously we have these particles. Of course, they're like what physicists call virtual particles. So they're very brief. Yeah. And basically, in quantum mechanics, anything can happen if you do it fast enough before it gets detected. So that's in some sense.
It's like in life.
Exactly. Yes. And it's that phenomena. So really thinking of empty space is already very challenging.
Right.
But thinking of empty space in the neighborhood of a black hole produces these kinds of.
Now that's the thing. You just said that it's so. I think you said it was so energetic around the surface of the black hole.
Yeah. So I think the point is this is happening right here, but these particle and antiparticle pairs, they pop into existence and then out.
Right.
And they can't stay in existence for very long, a very, very short period of time. But if you have a very powerful source of energy that can basically pry them apart and give them enough energy to materialize, to become real particles, then they materialize, become real particles, and fly apart. That's what the gravity does. If you're very near a black hole, there's what we call tidal gravity. You're pulled more strongly by the gravitational pull of the black hole at your feet. Mm-hmm. Than at your head, and it's stretching you.
Right.
So this pair of particle and antiparticle, they flash into existence and they're ready to disappear because they know they can't exist
they annihilate each other.
They're going to annihilate
right?
each other ordinarily, but this tidal gravity that would try to stretch you apart, it pulls them apart, gives them enough energy that they materialize, one of them flying out and the other one going in.
So what do we do with that radiation that's coming out of them? Do we study it? Do we learn anything from it?
Well, of course, it's...
Marfio was nodding his head.
Unfortunately, and you're asking me?
It wasn't you. No.
Raphael. Okay.
Well, I think it's important to keep the upshot in mind. So independently of the mechanism by which radiation comes out, what does it in the end boil down to? What it boils down to is that the black hole is boiling off. It's slowly radiating away all of its mass. It's fizzling away, and what you get in exchange is a cloud of what's called Hawking radiation. And in the end, that's all that's left of it. Now, that's not what would happen right now to the black holes that we see in our galaxy, because far more stuff goes into them all the time than Hawking radiation goes out. But if you left the black hole alone, put it in empty space and just let it be, and you gave it a lot of time, and you open your eyes again, what you see is this cloud of Hawking radiation and no black hole.
How much time is a lot of time?
A lot of time, a hell of a lot of time to use the technique. It really takes, but you know, and it's one of those questions that perhaps is not of some immediate practical importance to us, but it raises deep, profound questions about how nature works, because when Stephen first did this calculation, it seemed like this cloud of Hawking radiation bore no trace of any information about what made the black hole in the first place, and that
But you raised the idea that that I don't think we've heard yet, that a black hole can eventually evaporate. Now, this is after a certain amount of Hawking radiation occurs? Because not because it's giving stuff up, but because it's getting too many of these anti-particles.
That's really the same thing. You know, so one way, you know, it's like saying that, you know, if you owe somebody money, or you know, or your paycheck gets reduced, either way, you know, you're making less.
Right.
And it's really the same thing. It's like what would happen if you have a pot of water and you boil it for a long time, and after a while, there's no water left, and everything is just gone off in the air.
But it seems sort of, I don't want to, I'm just trying to understand this. If the Hawking radiation occurs because these paired particles separate a little right by the surface, and the antiparticle goes in, and the other one goes out, then you're adding to the diminution of the black hole.
Exactly. And you're as far away from this black hole, you don't really see what's happening with these negative mass particles that are falling into the black hole and making it smaller and less massive. What you see at the end of the day is a black hole getting smaller and a lot of stuff forming a cloud outside of it.
Now, if you have a really, how small a black hole can you have?
As small as about the weight of a gram of a corn of sand, so about a 10,000th of a gram.
A grain of sand? That's
yeah.
And would that last very long?
That one wouldn't last very long at all. It's those astrophysical black holes that we actually see, those would last for an extraordinarily long time.
So how long is not very long for a little black hole?
10 to the minus 43 seconds, so that's a billionth of a billionth.
No.
Much less than 1 second.
10 to the minus 43.
Yeah.
Yes.
Well, wait, let me get this. I have a...
Yeah. No, it's too late. It's gone already.
So there's no light coming out, right, of a black hole.
There is Hawking radiation.
Well, that's coming off the black hole from the way we've been describing it, not coming out of it. Because when you say out, in my mind, I think simply it's coming from inside it. But it's not. That's not good. The light is coming off the surface, right? I hope he doesn't mind our saying that. My saying it. But you can't see anything that's in there itself. So how did we first know it was there? What was the... If you can't see it, how did you know it was there?
The black hole?
Any black hole.
Oh.
Just theory pointed you toward them, or what?
So I think we should distinguish two kinds of black holes, the tiny ones,
Yeah.
for which the Hawking radiation is extremely intense. Almost paradoxically, the smaller the hole, the more intense the Hawking radiation.
And that's why it disappears fast.
That's why it disappears fast. I don't think those things should be called black holes.
Oh.
Because they don't behave like the black holes I study. My black holes are the ones up in the heavens, and they're gigantic. And the Hawking radiation is so tiny that you just forget it.
Yeah.
And so the black holes we look at in the sky, because the Hawking radiation is so extremely weak, it takes basically nothing to overwhelm it in terms of any gas or radiation falling in. So those are one kind of object, and then the objects for which the Hawking radiation is very intense. You shouldn't think of those are not things down which you fall and you're lost. They're things that pour out huge amounts of very intense radiation. They're dangerous to be around because they radiate you.
Can I, just parenthetically, can I ask you, when you talk about these big black holes, it's understandable to me that they're formed from big stars. But when you talk about one the size of a grain of sand, there are no stars that size, are there? How are they formed?
Well, you can think of, I mean, there are some people who think actually this might happen, that, for instance, if you shoot particles together, as you do in a particle accelerator, if in some sense you could make a very small but very intense concentration of matter, and then perhaps in certain theories these kinds of black holes can form. But indeed, as we were saying, they will immediately radiate.
Right.
So what you will have, you have something being formed, and then it will burst into pieces.
So that
looks very much what you have in a particle accelerator, because you shoot something,
yes,
something complicated happens. And then you have all the little bits and pieces, and then you try to reconstruct what happened.
So have these tiny black holes been, or have the effects of them been observed by scientists?
I think the most important effect was that people were very worried about them.
Yeah.
When the particle accelerator
Like the one,
in Geneva.
the LHC at CERN, people have been worried that black holes will be formed, but from everything we've heard, they would last only 10 to the minus 43 seconds.
They would think that it would.
But that could be enough time to do a lot of damage. Did I interrupt you before, Kip?
No.
So it's the other question is not only how did you find? Well, you were on the way to saying how you found them, but you find them through accretion disks and things like that.
So the first observational evidence for a black hole was an object called Cygnus X1, which was an X-ray source. You looked at it, you saw that there were X-rays coming off of something that was inferred to be an accretion disk. The gas had to be orbiting around something. The astronomers weighed that something because this object had a companion. So you could apply Kepler's laws to the orbit of the companion and weigh it, and discovered that this object weighed something like 10 times as much as the sun. And then you used what we understand about the fundamental laws of nature, which says that anything that is completely dark, but aside from the X-rays coming off this disk, it's pulling gas off of itself and to form this disk, but it's dark, and it's that heavy, and it's sufficiently compact to make those X-rays, it can only be a black hole. So that was sort of an indirect piece of evidence. That was a good enough piece of evidence for Stephen and me to make a bet.
Oh, tell us about that.
So this was our first bet.
Yeah.
I have a habit of winning these bets with Stephen. This is the only time I ever get on the front page of the New York Times is when I win a bet with Stephen. But this particular bet was whether or not Cygnus X1 was truly a black hole, and what was required.
Which side of the bet were you on?
Oh, I said it was.
Yeah.
He said it wasn't. But he said it wasn't because he had so much invested in it scientifically, that in its being a black hole. He wanted to have sort of an insurance policy that it wasn't a black hole. At least he got something.
So how was this settled finally?
Well, it was finally settled as the astronomers, and this is the combined work of hundreds of astronomers studying this object in great detail, ultimately build up a case that got stronger and stronger and stronger to the point where it couldn't be anything but a black hole. So I was in Moscow in, I guess this was 1990, and Stephen came out to Pasadena to give a lecture at USC, and snuck into my office and thumbprinted off on the bet. While I was away, I came back and discovered this wonderful concession.
Oh, that's great. That's great. So that leads me to wonder about not just discovering them, but once we know they're there, since it's so dark in there, we can't see anything. How do you, and I know, Andrew, you've really done a job on this, how do you get us to see, to visualize what's going on when we cross the horizon of a black hole?
The wonderful thing about Einstein's general relativity is it's so specific about the behavior of space and time and matter, enshrined in a very simple, on paper, set of equations called Einstein's equations. And if you solve those equations, which is a prodigiously difficult thing to do in general, but you can, in principle, solve those things and explore what Einstein's relativity predicts in various situations. It's a prodigiously difficult thing to do, but the theory is all there. You can ask Einstein's equations what's happening, and it'll spit out an answer. In the visualizations that I do, I didn't choreograph what was going to happen. It was a voyage of discovery for me to see what emerged from Einstein's equations.
That's really fascinating. Could you give a little example of that, of using an equation of Einstein's and suddenly seeing a picture come up? Did it work as simply as that?
Do you want me to do some stuff here?
Yeah, would you? That's great. Yeah, please. Do some stuff.
Do some stuff. I was going to say there's an ominous black screen, but apparently not an ominous black screen here. Can we bring up what's on this screen here right now?
There, what's that?
So you've all heard that we're going to see black holes today. Well, you're not. You're not going to see any black hole at all because, of course, a black hole is black, isn't it? So the star of this black hole thing is actually the stars that form the background to the black hole. In particular, this Milky Way here was taken by Axel Mellinger, who's given me kind permission to use it here. This is the most recent version of his all-sky Milky Way panorama. So Axel Mellinger, if you're watching, thank you very much indeed. This is rather an overachieving program. Let me start this going here. So, whoa. See what I'm doing here? This is doing full-screen general relativistic ray tracing in real time. And the people that we have to thank for this are not so much the scientists as the video gamers. So all of you out there who've been playing with your video games, thank you for all the gaming software and the hardware, because that's what allows this to happen. So let's see if we can find a black hole. It might be hard to find one here. Let's see if we can get one going here. Oh, that's good. Usually they're hard to find. This one here, though, I've imagined that this black hole, this is a spherical black hole. Now, real black holes are actually likely to be rotating, and they wouldn't look like this. They'd look kind of an elliptical shape rather than spherical. But it's hard enough to do these things with a spherical black hole. So we've got here a rather simple black hole, a spherical black hole. And I'm going to put on a couple of things here. First of all, there's a little map of where we are, just to orient you. Down here on the left-hand side, that's us. There's a green regime. It's not really to scale here. There's a green regime of safe, stable circular orbits. There's some yellow regime of unstable orbits, and then there's a danger regime, and then there's a red line here. And if we fall inside that, well, that's the horizon. Maybe we're going to get there. But first of all, let's stop this. Let's actually fire up the black hole flight simulator here. And so I'm going to go into a circular orbit. If you want to know how this works, there we go. We're now in circular orbit. This is now working in real time. We're orbiting the black hole. You can see that, can't you? It is actually working here, except I'm imagining this is the same mass as the black hole at the center of the galaxy. The reason I'm choosing that is we can go close to this black hole without getting tidally torn apart by the tidal forces, and that's a very wise thing to do. If we went near Cygnus X1, for example, we get within about 100 times the horizon radius before we got torn apart. So choose yourself a big black hole. Okay. So just to show you that we're really in orbit, here we are. On the right-hand side, you see a clock here, which is clocking our actual time in seconds. So you can see that there's 1,000 seconds going by per second. That's not because the black hole is distorting time here. It's just what we see on our watch as time goes by. And if you see it slow down, that's because I'm slowing it down. If it speeds up, it's because I'm speeding it up. If you want to find an explanation of what's happening here, I can offer you no better origin than Kip Thorne's book. His prologue describes the journey precisely like this, in Black Holes and Time Warps. When people ask me, where can I find out more about this? It's from your book, Kip, written almost 20 years ago.
I should tell you, I offered him a kickback this evening, but he declined.
So, as a special treat here, Kip, I'm going to fire you in into this black hole.
Oh, thank you.
Right here. And if you remember in your book, Kip, it was you sent in Arnold, right? Arnold was the robot that you fired in, and you were going to watch it. And I thought, well, yeah, the governor of California, probably a powerful person here. But what was his catchphrase?
I don't remember.
I'll be back. So how could you choose that? Arnold you sent into the black hole. The one thing he's not going to be is back. I need a little audience participation here. You can see the orange thing here. This is where we're going to throw Kip. We need a vote. Who thinks that Kip is going to fall into the black hole? Raise your hands if you think so. And panel, I want you to do this too, because I want to challenge you too. Okay? Who thinks?
How, he's that close to the edge?
Well, I'm going to fire. Let's.
So are we?
He's in it. He's going to fall in.
Is he going to fall in? Yes.
Yeah.
Raise your hand if you think he's
Thank you
going
very
to fall
much.
in. Thank you. Kip, go ahead. Good. No. Robert, you can lower your hand here. I don't want you to feel stupid here because we had half our panel say yes and half our panel say no. It's rather like Kip Thorne and Stephen here disagreeing. They can't even agree on something basic like whether a black hole exists. Let's see what happens here. So I'll fire it off. Oops. Let's take this back and slow it down because it happened rather slowly. Let's back up. This is something that you can't do, by the way, in reality. Even near a black hole, you can't. Let's bring him closer. Come here. And slow him right down. There we go. There we go. Now, Kip, you know that I took your photograph last night. Indeed, I took photographs of all of you, so you know where you're headed in just a moment. Here, it was my daughter who took those photographs, and this morning drew these portraits of each of you.
Oh,
so I thought it would be a wonderful thing. I think one of the highlights of this festival, at least for me, is the marriage of art and science that we're promulgating to you today.
So is your daughter in the audience?
Wild, are you there somewhere?
She should stand up.
Oh,
Stand
bravo.
up.
Good idea.
Let us proceed and see if Kip does his job by falling in like Arnold does. Let's speed him up. We have to. I've made him spin so that you can see how fast he's going. Well, At first cut, it looks like he's there in case you want to see. You can get out the telescope and say, bye-bye, Kip. Well, turn off the telescope here. Moral of this story, if you want to aim, you actually have to aim into a black hole. If you want somebody to fall into a black hole, you have to aim. They don't actually suck. You have to aim carefully. And you probably know which way I have to aim in order to send the next panel member in, right? Where do I have to aim, Kip?
So you're in a circular orbit?
We're in a circular orbit around the black hole, yes.
Yeah. So I guess you better aim backwards a bit. Aim backwards a bit, I hope. Am I right?
If you were a footballer, you'd know the answer, wouldn't you? You send it where the football's going to, the passer's receiver's going to be, right? So let's see if we can, let's see, who's our next panel member here? So I'm going to, it looks to me like the black hole is going down here, so I'm going to send, we lost Robert. Let's bring Robert back and slow him down. Robert gets quite excitable, you know. Let's come here. Slow down, slow down, slow down. You're upside down, Robert. I'm sorry about that. But rather a nice rendering, don't you think?
Beautiful.
Okay, let's send Robert in and see what his fate is. Go for it. There we go. That's a decent lick. Doesn't waste his time, does he? Missed. Whoa. Did you see some interesting gravitational lensing effects there?
Yes, yes.
Very briefly. It's hard to do this, by the way, because this is interactive. This is not pre-videoed. So sometimes you get it, and sometimes you don't. Let's try again. I think I have to fire even more off to the side here. And I'm going to slow this down a little bit so that we don't lose it. Come on, go for, there we go. Now, let's slow this down here. What do you see that all the members of this panel have in common?
We're extremely handsome.
We're extremely handsome.
Yes.
All white and all male, right? Which is, I think, this is a little bit sad. This is Vera Rubin, who was at the gala performance yesterday. And she was there. I come from an astronomical background, and seeing Vera always gives me a shiver up my spine when I see her. She was one of the very first women faculty members, and I'm rather proud as an astronomer that we have some women who go back a long way of having made pioneering discoveries. So I thought it would be appropriate, since we only have males, maybe it's appropriate to be sending males, white males, into the black hole, because we have a surplus of them. But I thought it would be appropriate. I don't know if Vera is in the audience here. Are you here, Vera? Never mind. She's probably doing something useful, some real astronomy and some speculation.
Didn't Vera discover dark energy?
She was one of the people who was one of the, not the discoverers, but charted out the rotation curves of galaxies to show that galaxies were full of dark matter.
That's what I mean.
Off you go, Vera. Let's see if Vera makes it to this exercise. Come on, Vera. You're a lot better than the rest of us. She did. She went in. So the women beat the men in this particular case. If you call falling into a black hole, beating the situation. If you didn't see her fall in, you can see here, this is her frozen and as we say, redshifted on the horizon, because the wavelengths of light that come off from her would be shifted into the red and infrared and far. Let me brighten it up a little bit, so maybe we can see Vera on the horizon and turn on the telescope here. Wow, look at that. There she is. Now, in reality, you wouldn't see Vera frozen on the horizon like that at all. That is her image. Can you see? That's Vera, frozen on the horizon. Now, from her own point of view, it's hard to keep up with this, isn't it? From her own point of view, she has fallen into the black hole, and all we are seeing is an image of her frozen on the horizon.
Why is she, would she, if she were...
Wow, did you see Robbert just go by?
Would she actually be frozen there?
She would appear, at least from a classical, non-quantum perspective, to be frozen on the horizon. Yes?
So is that just an optical illusion?
That's just an optical illusion. Let me just see. Who else has I got? Can I just see who I've got lined up now to fire into this thing? Because I think it may help. The next one may help us. Oh, look at this. Yes. This is Brian Greene, by the way. Slow this one down. This is Brian Greene. I have a little story about him. He has 3 eyes. He was also drawn by my daughter here. And we wrote a paper last year. When I say we, Wilde illustrated this, and a postdoc wrote this paper. Let's slow it down again. We were interested in 3D visualization of black holes. 3D is all the rage now, and we thought, well, let's do something nobody's done before, 3D visualization of black holes. And for me, it was a puzzling thing to do, because if you are in curved space-time and you look with your binocular vision, the trouble is the curved space-time curves the spherical light rays hitting your eyes, and you use essentially the radius of curvature of the sphere of light that's entering your eyes to determine how far away it is. That's how binocular vision works. And that is destroyed near a black hole because it curves space so much. And I thought, well, that's terrible. We're never going to be able to make 3D movies of black holes. Bad idea, right, Kip? You're going to make a 3D movie of a black hole.
We're working on it.
Well, I eventually realized that this is merely a limitation of people with 2 eyes. If you had 3 eyes, you could sort of triangulate the ellipsoidal wavefronts, and you'd be done. So I thought this was a wonderful thing. Let's send him in. And I want to, actually, you know what I want to do? Let's go down, visit the black hole. Let's go into a closer orbit, because aiming at black holes is a difficult thing. Okay.
Can you show us what it looks like inside the black hole
Yeah, we're going to get there.
that you got out of Einstein's equations?
Yes, we are going to approach the black hole and do that. There's Vera stuck on the horizon. And here we are in orbit around the black hole. Let's make this real time, I hope. There we go. This is real time. If you were in orbit around the black hole at the center of the Milky Way, this is going by around 1 second per second. You can actually see the sky move. Now, the black hole at the center of the Milky Way, 4 million times the mass of the sun, 10 times the radius of our sun. So that's a pretty big black hole. It takes just a few minutes to go around in the orbit of this thing. Okay, I showed you Brian Greene as a three-eyed person here. I want to show you one other thing here. Okay, so let's see what else we have here. You're going to come out. There we go. So this is the referee's report that we got on this article, and I'm going to stop it if I can right here. And the reason I'm showing you this, I wasn't sure that I should show you this, but I asked Kip Thorne in advance. He said you should show this. And it's a little moral story here. It says, this is a well-written, entertaining article, and I enjoyed reading it. However, although it does contain some new results, I feel that it's jolly black hole style and content, e.g. figure 11. Can you imagine what figure 11 would have been? It was the three-eyed ape. Would seem out of place in a sober professional journal like whatever it is. Moreover, it would largely be aimed at an audience. Sorry. Moreover, it would fail to reach the audience it is largely aimed at. So the reason I'm showing you this is I think there are real barriers between science and art. And some of those barriers, in spite of the present company, are coming from ourselves. We judge ourselves and we say, that is not appropriate for a science journal because it contains some art. Now, I think Wild, it was a magnificent piece of art. Okay.
So you're sending this review into a black hole, is that the idea?
That is correct.
You know how many times I wanted to do that myself?
This is one thing that we need black holes for. I do have,
But I'm eager to see the inside of this damn hole.
Just a minute, I have to get in control here. Alan is trying to avoid being thrown in.
Well,
So the main difference with Alan is I'm letting him be tidally torn apart as he falls in.
I'm getting longer and longer there.
And you got longer and longer and longer. Yeah. Okay, you want to fall in and actually
I want to look around in there, yeah.
Yeah, okay. First thing that has to be said is that Hawking's radiation has a profound influence on what happens here. What I've shown you here is people freezing at the horizon, but in reality, the wavelengths of light are getting very redshifted, very elongated, and the images of these people quantum mechanically would become as large as the black hole, and then their images would essentially be lost against the Hawking noise. I want to turn them off, and let's turn on something that you would not see in a real black hole, which is they don't really come equipped with a red grid. The trouble with black holes is when you fall through what we say is the horizon, there's nothing really there. It's like falling over the Niagara Falls. When you go over the Niagara Falls, there's a point of no return, and that's not where anything interesting happens. It's only when you get deep inside that something interesting happens. So let's fall inside, do a little reverse thruster maneuver here, and that should start us falling into the black hole. And let's see what happens. Whoa, yikes.
Now, what these look like a bunch of little whirlpools that you can fall into on the surface of the hole. Is that what you're showing us?
These little things here, you mean like this one here? That's just a grid that I painted on the surface of a black hole, like lines of latitude.
Well, are we looking at the surface, the horizon?
We're looking at the surface, at the horizon, this red grid.
So we haven't gone past the horizon yet?
We have gone inside the horizon.
Oh, we are. So we're now like in a narrow band within the horizon, is that it?
We're inside the horizon. We're actually a decent way inside the horizon.
Way inside.
Yeah.
So what's this grid painted on? Are we looking at the other? What are we seeing? What's the grid on?
Well, you remember I told you when I first started doing these things, I was completely perplexed about what happened.
Well, that's where I am now.
So welcome to the crowd.
Okay.
And it took me a year to understand this. So if it takes you a year to understand it, don't
Well, these people are going to be gone by then.
We have fallen through the horizon. The horizon we've fallen through is this bluish-looking grid above us, what we call the true horizon. This other thing here is actually an illusory horizon, which is a holographic image of what's inside the black hole. We'll get onto that later. When we go down to the horizon, we fall through the horizon, it appears to split into two. And the reason for that is once you're inside the horizon, essentially, space itself is falling faster than light. It's what Kip Thorne had to say, which is that time and space sort of change roles. Essentially, what's happening is space is falling faster than light.
Okay. Everybody here, including me, has heard that nothing goes faster than light. But in a black hole, space is falling faster than light. Why? What's going on? What is it about a black hole that makes space fall faster than light?
I would say a black hole is a place where space is falling faster than light. Let me. Which is a circular.
I would say red is blue. What do you mean that space? What do you mean by that? We'll say it again.
What I mean by space falling faster than light is if you attempt to come to a halt at this point, to stop falling to smaller radius, you would have to be moving. You essentially have to be moving through space faster than the speed of light. Space itself is falling faster than the speed of light. You cannot move through space faster than the speed of light. So the flow of space is what carries you inward
space
into the black hole.
That's different from me moving through space or anything moving through space faster than light.
That's
Nothing
right.
can move through space faster than light, but space can collapse faster than light moves.
That's correct, yes.
Well, that's a certainly weird thing that's happening in the black hole.
It's why light can't escape from a black hole.
Well, that's worth coming to a lecture for.
Should we continue?
Yes, go right up to the center. I can't wait.
Oh, I'm not sure that we're going to go through a center here, but let's go as far as we can, and let's see what happens. Now, this kind of black hole, it's a charged black hole. It's a surrogate for a rotating black hole, and what you're about to see is actually very similar to what you'd see in a rotating black hole. They have not only an outer horizon, but also an inner horizon.
Okay, so an inner horizon is like a globe within a globe, right?
It's a globe within a globe, yes.
So stuff that comes in from the outside, like dust or something, or an antiparticle, goes in, and what happens when it gets to the inner horizon, the inner globe? What goes on there?
We're about to see what happens at the inner horizon. What happens is that, which is something very remarkable indeed. So the outer horizon of a black hole is the place essentially where space is falling at the speed of light. It's like a waterfall of space, and the water is going faster and faster and faster, or space is falling faster. The horizon is the place where space is falling at the speed of light. Space is falling faster than the speed of light inside the horizon. But then in a rotating black hole, there's a centrifugal force which tends to slow the inflow of space, and the place where it slows back down to the speed of light is something that we call the inner horizon. And that inner horizon is the location of some very strange and energetic phenomena. If you like, this is the bottom of the Niagara Falls. Roger Penrose first pointed out in 1968, if you pass through the inner horizon of a rotating black hole, you will see the outside universe infinitely infinitely blue-shifted, infinitely energetic.
A particle particle coming in, going through the outer, the horizon.
Yes.
Goes faster and faster and faster. Water going over Niagara Falls goes faster and faster. When it gets to the bottom, that's equivalent to hitting the inner horizon.
That's right. That's right.
What's different about the speed of its descent or its movement?
Of the space.
Yeah.
So you're going with the flow. You're going down the Niagara Falls.
Yeah.
But when you get to the bottom of the Niagara Falls, the key thing is that water that's kind of bounced up from below is able to collide with the stuff that's coming back down.
Everything slows down there?
I wouldn't say it slows down. I'd say it speeds up.
Well, that's similar. It has some of the same words in it, you know.
Yes.
Okay, go ahead. I'm not interrupting. I'm trying to understand. Go ahead.
That's okay. It's hard enough for all of us to do this. But as Roger Penrose pointed out again in 1968, this is a place where light from the outside universe, what we're looking at in this is light from the outside universe, appears infinitely energetic, concentrated at the inner horizon. And now, if we continued on this journey, if this were an ideal black hole, the kind that Roy Kerr discovered in 1963 and as an ideal solution, mathematical solution to Einstein's equation, we could go through a wormhole and out to another universe. But in reality, this infinite concentration of energy at the inner horizon cuts off that wormhole physically. And instead of going through a wormhole to another place, we are vaporized by this instability.
Well, thank you very much. I really thank you. You mentioned, Andrew, and that there was really, I can imagine it must have taken you an enormous amount of effort to get from the equations to those fascinating pictures. But you did mention at some point there was the entrance of the idea of the hologram. Pick us up at that point, would you, Raphael? Where does the notion of the hologram come in this body, this black hole?
Well, we all know what holograms are. You know, you look at them.
Well, tell us again, because
they're on your credit card. They're on all sorts of cheesy things you can buy in souvenir shops. And what they are is you have a two-dimensional surface and you look at it and out pops this three-dimensional image of something or other. I don't know, Beethoven's head or the globe or something. And it's fun because it gives you this illusion that there's something hovering above the surface. But the reason we use this word in this context is as a metaphor for a situation where three-dimensional information is encoded on a two-dimensional surface. It's as if one dimension wasn't really necessary. All the information you need, you can fit on a surface. And what does that have to do with black holes, I suppose might be your next question. Why are these two things following each other in the title?
Yeah.
And that's a bit of a longer story, but it has to do with the deep questions that were raised by the fact that black holes can evaporate and disappear. So we mentioned earlier that if you leave a black hole alone, it's going to fizzle away, and what's left over is this cloud of Hawking radiation that it converted itself into. No more black hole, just a cloud of particles. And when Stephen Hawking first did this calculation, it looked like this cloud of particles was going to be exactly the same, no matter how the whole story started, no matter what kind of star collapsed to form this black hole, no matter whether atoms in the star were moving this way or that way or some other way, you could not recover that kind of information. Now, why do we care? It seemed like information was lost. Physicists care about that sort of thing very deeply. They care about global principles by which the laws of nature are organized. And until that moment, when Stephen did that calculation, there was a principle which is that information is never lost by any of the laws of physics that we know. By this we mean that if you tell me what the situation is now, I can predict with a big enough computer what it's going to be tomorrow, or retrodict what it was yesterday. It's like when you recover marks of tires at the scene of an accident, and you try to recover what actually happened. People are contradicting each other, and you're trying to figure it out. Who ran the red light? What actually happened? There's a general principle in physics that if you look carefully enough at some object, you can figure out what it was before.
So in this analogy you're using of a car accident, where the police will go and examine the tracks of the rubber on the road, maybe scrapes on the car, paint chips, glass on the. This is giving them information about what happened in a past event.
Right.
Now, how is that related to information in a black hole? What do you mean by that information? Because I think the word information means a lot of things to a lot of people. Can you tell us what you mean by information?
Well, I think the best way to think about information is the way that you tend to think about it in everyday life. How much of your hard drive is already taken up by your files. Well, those files represent a certain amount of information each. The total sum is how much space is taken up on your hard drive. If you have too many of them, well, you're trying to store too much information on that hard drive. And it's a very important concept in physics because it really tells you how complicated the world is. How much information do I need to describe a block of iron or a room full of air? And indeed, perhaps you can also ask the question, how much information do you need to describe any region of space and anything that could possibly happen there?
So that information was, the notion was that the information couldn't disappear from a black hole. And that was countered by the holographic principle, which says that you can actually retrieve the information?
The holographic principle came into the resolution of this very difficult situation. So I really want to emphasize first why people were so agonized about this.
Let me describe how agonized they were.
Yeah.
Stephen did this work while he was visiting me at Caltech in 1974-75. He wrote a paper saying if a black hole forms in some manner and then it evaporates, you lose all information about how it formed. He couldn't get the paper published. The referees said, this can't be. It violates the fundamental laws of quantum theory. It can't be. And so I saw him about 6 months later. We went to a conference in Chicago together. He said, I can't get the paper published. And I told him, keep trying, keep trying.
We don't toss out principles lightly in physics. Things that have worked everywhere.
Did not like a paper that said that there's something wrong with the laws of nature.
So he had information that disappeared.
That's right.
Yeah, right.
So he did ultimately get it published, and so go on.
It was as if every traffic accident left the same tire marks. No matter who crashed with whom, whether it was a red car with a green car, a truck with a bicycle, you get exactly the same pattern on the street afterwards. That's crazy, right? And not only is it crazy, it contradicts everything else we know in physics. And the reason people panicked is that it's very difficult to violate a general principle a tiny little bit.
Right.
It's very hard to do that. You have to explain why it's violated in this particular. What do black holes have to do with this? What's so special about them? Why do they get to do something that nobody else, no other object ever got to do before? How can we prevent this sort of disease from spreading all over the laws of nature? So, I'm just trying to give you the sentiment here.
Okay, so the holographic principle rode to the rescue here? Is that what you're saying?
That's right. There was a long debate, first of all. Is this information really lost or not? This claim was not made lightly.
For some 20 or more years, this became a conundrum that was a central tool in trying to understand how you unify general relativity with quantum theory. If anybody could really understand it really clearly, that would probably be a key step toward understanding this merger of these two fundamental theories.
Yeah. Now, there are two steps, really. When I make a black hole, and then I wait and let it evaporate. I'm a very patient person. I let it evaporate. And there's really, in both of those steps, do you have a danger of losing information? Now, historically, what happened is that the evidence accumulated that in the second step, when the black hole evaporates, turns into this radiation cloud, information is not actually lost. That made it more credible that it's also not lost in the first step. The first step is the place where you take something like a star or 10,000 elephants and you compress it into a black hole. And you want it to be true, if you're an old-fashioned physicist who believes in the preservation of information, you want it to be true that by looking at this black hole in some careful way, you can tell whether it was a star that made it or 10,000 elephants. And indeed, there was a possibility that this was true around the same time when Stephen discovered Hawking radiation. Jacob Bekenstein discovered that black holes contain information on the surface of the horizon. And now that's where the hologram comes in. Now, for everything to fit together, for it to be true that that information on the surface of a black hole was enough to remind us exactly which elephants went in or which star collapsed, it had to be true that the amount of information that fit inside the horizon was no more than the surface area, measured in certain units called Planck units, of the horizon. So you can imagine putting little tiny tiles on the horizon and labeling them 0 or 1 if you're a computer scientist and you measure information in bits. And there could not be more information in a region of space than zeros and ones that fit on a surface surrounding that region. And in the end, you can throw away the black hole. It had to be true no matter whether you turned the stuff that was in this region of space into a black hole or not. Who cares if I actually convert my elephants into the black hole? It's enough that I could.
Well, I want to get off the elephants and get onto the car tracks again. It sounds like you're saying that there are, to use the analogy, car tracks of some kind left on the surface of the black, the event horizon, right?
That's right.
What do you mean by that? Take us from that analogy to something a little more concrete, because it sounds to me like something goes too close to the event horizon, it starts zooming into the black hole. There's maybe some flash of light or something that
Unfortunately, the question that you just asked is among the hardest in physics right now.
That's what I'm here for.
Too bad. But yeah, so the funny thing is that we've known since the mid-'70s how much information fits on the surface of a black hole, and we have great confidence in that number. But it's much harder to say what the actual objects are that are carrying that information. Are these little wiggles that sit on the surface?
It's something you can read, you can.
The best way to read it is to let the black hole evaporate and then measure the radiation. It's like, it's like something's locked in a box. Best way is to open the box, let it come out, measure it. But that doesn't mean that your question wasn't an important question. It's one of the most exciting areas of research to understand what it is before.
So you've said see if you can make it work with this question. You've said two things. One, that there's information on the surface of the hole. And the other is the best way to measure the information is to let the whole thing evaporate and then measure the radiation. That sounds like two different things to me. Well, one is that there's information there, so how come you can't read it if it's there? You have to wait till it goes away to read it.
The real question that I'm trying to get at is whether the information has already, never mind whether you read it or not, you can ask whether it has somehow been erased.
Okay.
Right?
You may not be able to read it at the moment,
if it was true, as we might naively think, that the amount of information in a region of space grows like the volume of the region. You know, you have computer chips that store your hard drive, whatever, some bits of information. You can pile them up into a big pile. Now, if you make the volume of the pile twice as large, you can store twice as much information in those computer chips. Yeah. Right? It goes like the volume. It has nothing to do with the surface area of the pile. Who cares, right? You're filling. But fundamentally, it seems to be true that the surface area gives you the absolute limit of how much information you can store. If you try to do better.
You were going to add to that.
Well, I mean, I think it's important to stress that, it's a principle. It's not yet a fundamental theory, because what we're seeing is if you want to marry general relativity with quantum theory, we have this huge problem. And we know the principle to its solution is this idea that there are extra degrees of freedom, some extra stuff that's not in Einstein's theory, which is sitting close to the horizon. It's basically this hologram. So you need some kind of a theory that really has both of these ingredients in it. And for instance, string theory is one such theory. And there are certain models in string theory that actually precisely do what kind of the doctor ordered in this case. And so there we can actually literally see this information in the black hole, and we can see the evaporation. These are not the kind of models yet that we would like to use for the astrophysical objects. But to really answer this question in full detail, we need this kind of theory of everything, where all these phenomena are acting together. And that's why it's such an extremely important question, because a full, satisfying answer really requires such a fundamental description of nature.
So you can get information from, the information is encoded somehow on the surface of the black hole that tells, if you can read it, if you could read it, what's gone into that black hole in its history. Does this apply to any other parts of the universe? Does this apply to our universe as we know it? Is there some event horizon here that has all the information about us?
Well, actually, yes. Yes, that's a big topic, but there's a sense in which we live in an inside-out black hole.
We live in an inside-out black hole.
There is an event horizon that surrounds us, and it comes from the fact that the universe seems to be filled with something called the cosmological constant, or dark energy, which is driving the acceleration of the universe the expansion of the universe to accelerate. It's like you're on the gas pedal. We used to think that we're on the brake, but actually we're on the gas pedal. It goes faster and faster apart. And as a result of that, things that are far enough away from us, they're like something that's crossed inside a black hole. They're in a place where space itself is receding so fast from us that not even light can travel back to us from there. So there's a sphere of no return surrounding us in the universe. And all of the questions that we're confused about that have to do with black holes and information, we have to ask again about that sphere, and we're even more confused about it.
Okay, you know what? We had a late start. That's why I let us go longer than the announced time. But I do think we have to break up now. I do believe that some light has been thrown into dark places by tonight, thanks to our very wonderful panel and to the great Stephen Hawking. And thank you all for coming.